Yeah, Assalamu alaikum. Again, welcome back to this lecture series. And we're going to move on to the lecture number 2 on ceramic nanostructures. And so this is part B, nanostructures by surface modification. So I'll talk about some surface modification technique that you will see is pretty inexpensive and can be done in any lab. So I call this nanotechnology by materials design. You'll see that one can exploit the intrinsic material properties to create ordered and oriented nanostructures on the surface of the material. So it's inexpensive because it's non-lithographic, no need for E-beam, X-ray beam lithography. Those are expensive. No need for a highly trained technician to maintain those. Simple setup like furnaces and gas cylinders. Highly scalable in the sense that you can cover the entire surface, bulk scale surface, in a single step. And obviously, eventually this surface patterned or patterned surface can be used for application like gas sensing, catalysis, or biological cell interaction on the surface. So I'm going to talk about surface nanostructures in oxide ceramics by a gas phase reaction. So today's topic is that, and I'll start with some references I give you in case you want to read more about this topic. So the first work was started in titanium dioxide rutile. So it's a well-sintered TiO2 rutile structure, which was then exposed to hydrogen-nitrogen gas mixture at around 700 degrees C. And this structure actually turned into this. You can see on the surface, it's a nanofibrillar structure. Taking a closer look, you can see that this is turning into something like that. And you can see within a grain, these fibers are oriented along a particular direction, happens to be 001 of the rutile crystal structure. So this is amazing that you convert this surface, you're basically etching the surface by gas phase reaction, in this case, hydrogen gas. So we look at the rutile, TiO2 is made of this TiO6 octahedron connected in various ways. So this rutile is the two-edge shared TiO6 octahedron, whereas anatase is the four-edge shared. 4 edges are shared. So you can see because of this sharing and how these octahedron are connected, making the three-dimensional structure, there is a distinction between rutile and anatase, and also there is a phase called brochide, which are both edge and corner shared. Anyway, so these are different polymorphs of TiO2, and in this case, we are working with rutile TiO2. Now so one of the question is that we create this in hydrogen-nitrogen environment. So we start with rutile TiO2. We are making this fibers is still rutile TiO2. And XRD-XPS indeed confirms that it's a rutile TiO2. It's not quite TiO2, it's TiO2 minus X to be precise. And then selected area electron diffraction also confirmed that nanofiber are rutile, and fiber orientation in TM is determined to be 001. So if you look along the C-axis of the rutile structure, you'll see that there are rectangular holes running through along that direction. So initially we thought that there is diffusion anisotropy along that direction, but looking at the data, the diffusion anisotropy in that direction is not very different from the other direction. On the other hand, on the 001 surface, there is strong reaction anisotropy, and I'll talk about that. So you can see that this is a single grain, these are single grains, and preferentially, so this is some initial stage of etching, preferentially the 001 face is being etched. So what is the mechanism? So what we think is hydrogen is reacting with TiO2 and breaking the bond on the surface, Ti-oxygen bond, and taking oxygen out as H2O. So a natural question is, what is happening to titanium? Oxygen is being yanked by hydrogen, creating H2O, which is going into the vapor phase. And through various experiments, including wet loss and the MSGC, mass spec, and gas chromatography, we confirmed that titanium is not going to the gas phase. It's actually diffusing into the bulk. So there are some internal sinks. It's actually one titanium can be accommodated per 800 units up. So, in the bulk, there is plenty of titanium sink. And as oxygen is taken out, titanium moves into the bulk. So you create a gap, and that is creating this space between fiber, empty space between fiber. So if that's the mechanism, then one might argue that why doesn't the hydrogen reaction uniformly etch the surface so that the top surface keeps on receding gradually? Why do we get this anisotropic structure, meaning etching is happening not everywhere, obviously. Some parts are protected. And we found the answer by doing this TM analysis. So we were able to separate the fibers as well as the tip. You can see the tips of the fibers are very distinct. These are the tip material. And in TEM, we do the chemical analysis. So we see, besides titanium on the fiber, we see copper. Copper is coming from copper grid. So we spread this on copper grid for doing TEM, basically. So, and if we look at the tip material, we can see besides titanium, there is iron and nickel. Again, copper is coming from the copper grid. So where is this iron and nickel coming from? Iron and nickel is coming from the hundreds of parts per million level impurity of iron oxide and nickel oxide that we have in the commercial TiO2 powder. So during the hydrogen-nitrogen heat treatment, these segregate to the surface. They reduce it to metallic particle, and these metallic particles are now acting as protective cap. So etching goes around it, and the etching is anisotropic because the bond breaking energy, so breaking the bond, titanium oxide bond on the 001 plane is the easiest compared to the other surfaces. So the bond breaking and taking oxygen out is anisotropic along the 001. So again, to summarize, you can see that we are basically primarily etching in between fibers, and the fibers are protected by the metallic cap that is created by the impurity in the material. Then in tin, we can do gold catalyzed growth, like PLS type mechanism. So what we do is we take a single crystal 001 TiO2. First, we put a sputtered layer of gold, a very thin film of gold. And during the hydrogen-nitrogen treatment, the gold actually de-wets and forms gold spheres. And then in the hydrogen-nitrogen environment, we actually grow this TiO2 fiber. So there is growth vertical, perpendicular to 001 direction, as well as by tilting the sample in TM, you can see in-plane growth as well, 110 direction. So we do the same thing. We can do the same thing in tin dioxide. So this is tin dioxide polycrystalline. In this case, you can probably recognize one grain here, another neighboring grain there, and so on. So we start with the well-centered polycrystalline tin dioxide, and we first put a layer of sputtered gold thin film, and then we do the hydrogen-nitrogen treatment around 720 degrees Celsius. And you can see that during the treatment, the fiber is growing with gold at the tip. So gold is a marker. And you can see this grain has different crystal facets, crystal orientation, and on each facet, all these fibers are actually parallel, which is expected. So what is the mechanism for this growth fiber in the gold catalyzed case? What we believe is that during the heat treatment around 720 degrees C, tin dioxide is actually creating tin monoxide vapor. It can also create tin vapor, but if you look at the thermodynamics and do some thermodynamic calculation using delta G naught of this reaction, you can find out that the partial pressure of tin monoxide is 2 to 3 orders of magnitude higher than tin vapor. So we believe primarily tin monoxide is being vaporized from the substrate, and then that tin monoxide vapor is absorbed onto that gold particle on the surface, and then further conversion to that would be oxidation of tin monoxide to tin dioxide. And we do this in humid environment, because if we do this in dry hydrogen-nitrogen environment, then tin dioxide would be reduced to metallic tin. So to keep the tin dioxide in the oxide state, we have to introduce some humidity. So your hydrogen-nitrogen gas environment is bubbled through water, so it carries some water vapor that raises the PO2 above the oxidation boundary between tin and tin dioxide. So this is an interesting process. So far I have shown you that I grow either grow or etch nanofiber and nanostructures of the same material that is same as the substrate that I start with. There is some work done by another of my students, where first tin dioxide nanowires were grown on commercial fluorine doped TiO2 slides. So these are commercial substrate that is available. So we used a VLS technique that I talked about in the first nano lecture to grow tin dioxide nanoware. So there's tin dioxide nanoware along the core here, tin dioxide nanoware here, tin dioxide nanoware along the core. And then this FTO substrate with the one-dimensional tin dioxide nanoware was immersed into a hydrothermal chamber containing titanium solution, titanium precursor solution. And during the hydrothermal process, it actually grew this TiO2 nanotinsels. So this TiO2 nanotinsels are growing on top of the one-dimensional tin dioxide nanoware that was grown by VLS. So this is an interesting structure in the sense that the gas-solid interaction or catalysis could be done on TiO2, and the electrical conduction pathway can be separate. So the electrical conduction pathway can be tin dioxide, and the reaction or interaction of whatever we are trying to detect can be done on TiO2 nanotinsels. So in electronics application, people are looking for this kind of nano-hetero structures. So if you look at the details, we did all the details of the TM image of pristine tin dioxide nanoware. And you can see, we can figure out from electron diffraction, we can figure out the direction of the tin dioxide that we grow on FTO substrate as 010, and then we do the cross-sectional TEM. So here you're seeing tin dioxide nanowire along the core. And these are the TiO2 nanotinsel that we grow onto. And the nanotinsel's growth direction is 001. And then if you do an atomic model, which is being shown here, so this is your tin dioxide rutile structure grown along the 101 direction on FTO. And then TiO2 nanotinsels are growing along 100 direction. So it should make an angle here of 33 degrees, which you can measure in TEM, and you can actually confirm that indeed it's making an angle of 33 degrees. Moving along, so I give you some details about the processing conditions. So the VLS condition to grow the tin dioxide nanofiber first on FTO slide, and then this gives you the hydrothermal condition, processing condition in a titanium precursor. So titanium precursor in this case is titanium butoxide. So these are details, and this is where we, publish this. So then I'm going to move on to another technique. So far I have shown that you take the substrate, oxide substrate, and either etch or grow oxide on top of it. Now I'm going to talk about another work by one of my students who said, okay, can we take metal, something like titanium or titanium alloy, and grow one-dimensional oxide by some special oxidation process. We're going to do this in argon environment that has tens of ppm of oxygen. So we are basically oxidizing, we are going to oxidize metal in a deprived oxygen environment. So basically we do it in argon. You put your substrate like titanium alloy bulk or foil or thin film or even titanium alloy particles, and then flow argon gas that contains tens of ppm of oxygen. We can do this in bulk, foil, thin film, and particles, and then basically flow the argon gas, and you will see that we will be able to grow one-dimensional TiO2 by special oxidation process. So here's an example of TiO2 grown on beta titanium alloy foil. So this is 5% aluminum, 5% vanadium, and 5% molybdenum alloy elements. And, for titanium, you can find all kinds of commercial alloys. We do expose this to argon environment, and now you can see that you can actually create this nanofiber oxidized TiO2 in this form. This is interesting. So you start with the foil, and you cover the surface of that foil with this one-dimensional oxide. There is some, optimization that you can do. So, for example, you can control the temperature and you can control the flow rate of argon gas. And we found out when the flow rate is low and temperature is low, we don't get much of fiber, very short fibers. And then this is the optimum condition. So it actually does not depend too much on the flow rate, but it's sensitive to temperature. 700 is the sweet window. We grow a lot of nanometers. Then if you increase the temperature a little bit to 800, you can see in addition to nanofiber, we are getting equiaxed growth of titanium oxide, which is what happens in air. So if you took your substrate and exposed it to air, you would see this equiaxed oxide growing on the surface, simply by oxidation. We also further confirm that if you go to even higher temperature, 900 degrees, you see only equiaxed oxide, fibers are gone. So there is a sweet window, and from this, we figured out that as you're increasing the temperature, you're actually increasing the probability of oxidation from other surfaces. So while at 700, you preferentially oxidize on the top, so you keep on growing one-dimensional structure. But as you go up in temperature, you are also oxidizing from other surfaces. So it prefers this equiaxed growth rather than an isotropic. This is interesting that while at high temperature, you cannot start the one-dimensional fiber, but you can sort of change the temperature in the process. So what I'm saying is that at 700, you grow nanofiber for a while, and during the process, you raise the temperature to 800. So this part is grown at 700, and this part is grown at 800. And then you lowered the temperature, and this part is grown at 600. So you can see that this is also this cat-tail type structure, cat-tail growth, is confirming that the growth is happening on the top, preferentially on the top surface. So this one-dimensional nature and isotropic nature is maintained. But you can see that the diameter of the fiber is increasing with temperature and decreasing with temperature, and you can see lower temperature. So that means obviously at 800, you will not only you are going to grow oxidation along that direction, but you will get some oxidation in the lateral direction, so the diameter increases. So this is an interesting process that you can control the diameter and length and so on. So one question that we struggled with is that why is it forming one-dimensional oxide and not covering the entire surface with an oxide layer? Indeed, if you exceed the oxygen content in your gas environment more than 100 ppm, we have seen you actually grow a thin film of oxide. But if you would deprive the oxygen content to tens of ppm, then you grow this one-dimensional oxide. And we were able to confirm the reason for this in Ti6-4 alloy, for example. Titanium 64, 6 for aluminum, and 4 for vanadium alloying elements. In the Ti6-4, when we cross-section and do a TEM on one of the fibers, you can see there is a core, and the electron diffraction confirms the core to be a rutile TiO2. And there is a clad layer, shell layer, see that clearly, and the electron diffraction matches the aluminum oxide. So what is happening during this process, aluminum from the alloy segregates to the surface, and aluminum is more oxidation prone than titanium actually, metal. So aluminum oxide forms on the surface, and that actually prevents further oxidation on the lateral surface. So the oxidation happens preferentially at the tip, and TiO2 will keep on growing, and aluminum oxide as a shell protecting the one-dimensional growth and isotropic. You can see some cartoon of the mechanism that I copied from the PhD thesis of my student Ben Tynan, that you basically create a thin layer of oxide, aluminum oxide first, that so your titanium has to diffuse along the grain boundaries of aluminum oxide layer, come in contact with oxygen and form TiO2, and then alumina layer keeps on growing along the surface, and you keep on supplying titanium from the substrate and keep on oxidizing from the nutrient, which is oxygen in the argon gas. So extension of this oxidation process to other systems. or I should say other type of structures. You can see that you can do this in titanium alloy particle. So these are particle, and you can see the surface is covered with the oxide nanofibers. Higher magnification shows the TiO2 fibers very well grown, and you can see interparticle contact. So if you place this particle close by, then you'll get fiber-fiber contact. And this gives an idea of designing gas sensors. So on a sensing platform like this, interdigitated gold electrode printed on alumina substrate, you can sort of initially distribute the titanium alloy particles on that platform, and then do this argon treatment where you grow this TiO2 nanofiber. Now this becomes your sensor, where you can do gas interaction on the TiO2 fiber, and the signal would pass from titanium alloy particle through the TiO2 fiber, where the gas is interacting with the neighboring particle, and the signal would be carried. And you can see that you can contact fiber-fiber contact, create fiber-fiber contact by strategically positioning this titanium alloy particle on the sensing platform. This gives an idea of creating interesting p-n junction. So, for example, you can take titanium particle with p-type dopant like aluminum, or n-type dopant like the nickel, not nickel, but tin or some other n-type dopant. So in that case, one of this TiO2 would be p-type, the other would be n-type, and you can create this kind of interesting p-n junction of the nanofibers, and that would give you probably some interesting application or device. So you can see if you take a titanium grit that people often use for doing microscopy that are available with holes, these are titanium. Then by doing this argon process, you can see that you can create this TiO2 nanofibers. And this would act like a reaction cell. For example, you can flow some gas through these holes, and then your gas may come in contact on the nanofiber, and you may be able to do catalysis, for example, by adding catalyst to this fiber and catalyzing the gas, like the catalytic converter I talked about earlier before. We actually found this work was done in collaboration with Professor Hasib, who was at that time at University of Malaya in Kuala Lumpur. Now he is here. And his idea was that, can deformation enhance this process or plays any role in this process? So his student did some crude experiment, took a titanium alloy bar and basically hammered it and create a different degree of deformation, least amount of deformation. And then as you keep going from 1 to location 2 to location 3 and location 4, the degree of deformation is increasing. And then he basically did this argon treatment on this deformed titanium piece. And then he saw that in position 1, position 1 is undeformed. And as you go from 2 to 3 to 4, the degree of deformation is increasing. So in the undeformed form, you basically grow equiaxed oxide. And then if you go to position 2, you see some one-dimensional structure on top of the equiaxed. Location 3, more, and location 4 is even more. So clearly, the deformation pre-deformed sample is enhancing the process. So what we believe, and this has been published here, what we believe that this deformation is providing an additional driving force for diffusion of titanium. So if you deform, diffusion of titanium out of the substrate and coming out through those alumina grain boundary and reacting with oxygen, so that deformation is enhancing that process. So clearly you can start with deformed sample, or if you're using particles, you can ball mill. That will introduce some deformation, and that should enhance this process. We actually did some experiment on commercially pure titanium. The commercially pure titanium in dry argon doesn't work very well. The fiber growth is not very robust. But if we do it in wet argon, we pass argon through a water bubbler and let it carry some humidity, and then we see that all kinds of interesting things happen. You can see these are stacks of TiO2 octahedral units that are stacked on top of each other, and then it changes the direction, and it forms all kinds of interesting structure. You'll see, looks like a, sword or something like that, and so different types of structure. So different kinds of morphologies are seen. There's two different morphologies. These are at the base. These are along the fiber, interesting structure. And then these also, the stack layer observed in this process. So in the wet argon process, the commercially pure titanium, which is not as robust in dry argon, in wet argon, it's very robust. We don't understand all of this, obviously. Many things are happening. Here's another thing that we did. So we grow this one-dimensional TiO2 in argon environment, and then collect those one-dimensional TiO2 and put it in a hydrothermal environment containing barium source. And we grow this barium titanate that looks dendritic. So we are basically converting the TiO2 into barium titanate in the hydrothermal environment, making barium titanate, which is a ferroelectric environment. So you can see that this dendritic barium titanate has this four-fold symmetry, and it's an interesting structure. So people have, made barium titanate in different forms, including thin film. The question is, this anisotropic form of barium titanate as a ferroelectric, would it have any particular advantage? That's something to be seen, but this is one structure that we can grow. For example, this can be used as a sensing material to preferentially selectively detect polar molecule like acetone compared to non-polar molecule like CO and oxygen and so on. With that, I'm going to summarize so that, by the way, this gives you actually details of this, wet argon treatment and growing these different types of nanoware, and then the hydrothermal conversion of the barium titanate. You can see it's using barium-containing solution in the hydrothermal environment, create those, those kind of structure. So in terms of future outlook, gas phase reaction can be used as obviously an affordable manufacturing route to design ordered and random surface nanostructure that can be used as platform for various applications like gas sensing, catalysis, biological cell interaction, etc., biomedical or bioengineering. This process is very simple that uses moderate temperature furnace and gas cylinders, so it can be done in any lab. Applicable to wide range of materials, you can do oxide on oxide, you can do oxide on metal alloys. This provides an opportunity for designing 1D, 2D, and 3D hierarchical heteronanostructures with opportunities for fundamental studies as well as application sensing catalysis, biomedical, battery, electrodes, even photovoltaics. So with that, I'm done with this lecture, and we'll move on to the next lecture in the next lecture.